Hello friends, welcome back to Statistics for Thesis Writing course. I hope you are all doing well and having a great time. In episode 4, we check the assumptions for our health and environmental examples. Here's the link at the top right corner of your screen if you haven't seen it yet. And we did the same for the psychology example too in episode 5. Now we can finally move on to the part that most students are waiting for: how to actually read the statistical outputs. We are going to look at the results from our models, understand what the coefficients mean, look at p-values, potential confidence intervals, model fit, and most importantly, learn how to distinguish statistical significance from practical significance. But before I interpret the health model outputs, I want to add 2 more important diagnostics that I forget about in episode 4. They are especially relevant to logistic regression. So a quick reminder in case you forgot the health research question. The question was, which demographic and lifestyle factors predict hypertension? Because hypertension is a binary outcome, yes or no, we used logistic regression. We already checked several important things, including multicollinearity, but logistic regression has a couple of additional considerations that we need to understand. First additional assumption is linearity in the logit. You may remember that when we discussed linear regression, we talked about the linearity assumption. But with logistic regression, the idea of linearity is slightly different. We don't require hypertension itself to have a straight line relationship with the predictors. No. Instead, for continuous predictors such as age, BMI, and cholesterol level, we assume that their relationship with the logit odds of hypertension, pay attention, not the hypertension itself, with the log odds of hypertension is approximately linear. So, this is, as I said, is called the linearity in the logit assumption. One way we can check this is with the Box-Tidwell test. Here, run the test. And the important result here is the p-value. As you can see, these are all greater than 0.05, even the overall test's p-value. So we don't have an evidence of violation of the linearity in the logit assumption. So one more time, just to make sure that you understand, logistic regression does not require the outcome to be normally distributed or linearly related to the predictors. Okay, so now the next assumption that I want to show you is Cook's distance. Cook's distance helps us identify observations that have a relatively large influence on our fitted model. We can visualize it with plot function, and then also add a commonly used screening threshold. So run it. And as you can see, these are influential observations, the one right above the threshold line. And with this line, you can also see the exact numbers for it. So run it. And here you go. So this result says that in our data set, these observations deserve further investigation. Please notice the wording that I used. They deserve investigation. So we do not say these observations are outliers, so let's delete them. No, that's not how we should handle influential observations in a real thesis. An observation can be unusual, but still can be completely legitimate. So anyway, this was one of the most important habits in statistical analysis. We check those observations before, and for this example, we just keep them. Now that we're done with those left-off assumptions, let's start with today's business. We will interpret the results, the outputs, and we're going to start with health example. And for the next episode, we will move on to the environmental and psychology examples as well. And first, in the council window, look at the outcome distribution. We have 130 participants without hypertension and 170 participants with hypertension. So approximately 56.5% of the participants have hypertension. Now look at the model deviance. the null deviance is 389.68, while the residual deviance is 282.32. So how do we interpret this? In statistics, deviance is a goodness of fit statistic for a statistical model. So we often use this deviance in a statistical hypothesis testing. And the null deviance result is for the null model, which is the model without our predictors. And after adding the predictors, we will have the residual deviance, which in this case shows that the deviance decreases substantially. So we can safely say that our predictors provide a substantial improvement in model fit compared with when we have only the intercept model. Move on, then we have AIC of 298.32. But remember, we don't look at an AIC value and say, okay, AIC equals 298, so the model is good. No, that's not how it works. AIC is primarily useful for comparing competing models when they are fitted to the same data. So here, in this situation, we only have one model, the logistic regression. It's not useful here. But in general, for your information, when you have several models, a lower AIC generally indicates a preferable, better balance between model fit and complexity when comparing them. Now we get to an important point, the coefficients. The coefficients from logistic regression are not shown in log odds format. Log odds are not very intuitive, so in order to get the right interpretation, we usually exponentiate the coefficients. So one more time, exponentiating will give us the odds ratio themselves. Let's start with age. For age, the coefficient is 0.097 with p-value less than 0.001. Get an exponential function from it, and there you go. It's 1.103. It means that holding the other variables constant, each additional year of age is associated with approximately a 10.3% increase in the odds of hypertension. So this relationship, this association is statistically significant. The next variable's association with the outcome checking is for sex. For males compared with females, the coefficient is negative 0.5467 with p-value of 0.06. So as you can see, the odds ratio is approximately 0.579. So this number means that the estimated odds of hypertension for males are about 42% lower than for females, considering that we hold other variables constant. However, as you can see, the p-value is greater than 0.05. See, it was 0.06. Because of that, we conclude that we do not have sufficient evidence at the conventional 5% level to say that sex is associated with hypertension in this model. Right? That's an important point that you should always consider. A point estimate can suggest a direction without providing a strong enough statistical evidence for that relationship. So don't just rely on the numbers amounts. The next variable's coefficient is for BMI. BMI has a coefficient of 0.115 with p-value of 0.00021. And as you can see, the odds ratio will be 1.121. This number says that each 1 unit increase in BMI is associated with approximately a 12.1% increase in the odds of hypertension, considering that we hold other variables constant. So the association is statistically significant for BMI and hypertension. Then we get to smoking. The smoking status has a coefficient of 1.7378 with p-value of 2.49 multiplied by 10 to the power of -6. It's a very small number. And as you can see, the odds ratio would be approximately 5.68. So what does this number say? It says that compared with non-smokers, smokers have approximately 5.7 times the odds of hypertension after, of course, adjusting for the other variables in the model. So this is a strong estimated association, and it is statistically significant. But remember, an odds ratio does not prove causation. We're just only describing an association in this model, not causation, okay? Next variable is physical activity. Physical activity is categorical, so our compares its categories with a reference category. Here, the reference category is high physical activity. We have 3 categories in total: low activity, moderate activity, and high activity, okay? So for the low activity group, the coefficient is 0.9657 with p-value of 0.0172. We're going to get an exponential from it to get the odds ratio, and it is approximately 2.63. So compared with the high activity group, the lower activity group has approximately 2.63 times the odds of hypertension. Of course, considering that the other variables are constant. We can say that the association is statistically significant. For the moderate activity group, the coefficient is 0.87967 with p-value of 0.0107. And the odds ratio, as you can see, is 2.41. Compared with the high activity group, the moderate activity group has approximately 2.41 times the odds of hypertension, considering we hold other variables constant. So again, it says that it is statistically significant. But notice something subtle here. We cannot say that low activity is significantly different from moderate activity just because both coefficients are significant. No, each is just being compared with the high activity reference group. Is it clear? And the last one is cholesterol level. The coefficient for cholesterol level is 0.01445 with p-value of 0.00294. And the calculator gives us an odds ratio of approximately 1.0146, which means that each 1 unit increase in cholesterol is associated with approximately a 1.4% increase in the odds of hypertension, considering that we hold other variables constant. So from this video, for health example, we found significant positive associations for age, BMI, smoking status, physical activity categories, and cholesterol, while the evidence for sex did not reach the conventional 5% significance level. Right? So that was it. That was today's video for the interpreting the outputs of the health example. We just interpret the numbers, not the real meanings in the context and what they mean. It's going to be another episode to cover that episode after we interpret the results for the psychology and environmental examples as well. So as always, thank you so much for watching my videos, friends. If you have any questions, you can drop it in the comment section below. And if you like this video, please click the like button and subscribe to my channel. I'll see you in the next video.